Okay, video for today is started. All right, let me get this a better size. All right, and we can move that somewhere. Do I need to have my picture up there? Probably not. And this annoying thing. That's gonna mess with some of our real estate a little bit. Maybe not. Okay. Layer. I will make sure to get here earlier so that we don't have to deal with this. Okay. All right, we are on to 1.2, right? Because that was 1.1, which was rather long. Okay. I think the most important thing on 1.2, we will go over again because it's just super important. And that was the thing where we talked about the field point and the charge point, right? Do you remember that? Okay, because it's a little different now. Let me just back up on that. I think I said this in the video, but you are used to dealing with, like the electric field or the force from a charge, as if the force, as if whatever that charge is at the origin. That's what you're used to, right? And so you never have to deal with these kind of two vectors, one vector that's pointing out to the actual charges in space, wherever they are, and one vector that's pointing out to wherever you're interested in having the field or the force or whatever, right? You never had to deal with both of those before, because in 116, we just say, like, just let all the charges, whatever charge there is, let one of them, at least one of them, be at the origin, and then you're kind of like looking out to the other ones to get like the force between two charges or the electric field due to one of them, right? So you are never having to deal with the second vector, but it's super important. It does kind of up the complexity a little bit, and we'll see that, okay? And in your book, just to reiterate that again, in your book, the symbol for the difference between those two vectors, do you remember what I said about it in the video? It's script R. It's a weird square script R, right? Like a old time cursive R, right? Okay. You might be the last generation to actually know what cursive is. Anyway, but it's kind of like, that kind of thing. And it's bold because it's a vector, right? Which I can't do on here. Okay. But when I'm writing it in class, as we said before, it's going to look like this, omega, because I can't draw that thing every 5 seconds. I just can't. It'll be a disaster. Okay. Everybody good with that? All right. Well, I just wanted to reiterate that. Maybe a little bit down. All right. Okay. It's gonna be fun. All right. Let me get oriented on what we're going to do. We are going to look at differential calculus today. Okay. This just means taking derivatives, but really, we're going to be dealing with the derivatives that we take of vectors, right? And this is all that Calc 3 stuff that you know and love, I'm assuming. So let me move this. I guess I can move this thing down to the bottom. See if that works better. And maybe, let's see. Be nice if it just stayed that little tiny thing, but it kind of doesn't want to. Won't look like it. All right, let's see if I need to stop that. Way down here. Okay. All right. Cool. All right. So differential calculus. Okay. So you're all familiar with ordinary derivatives, right? The regular old things. If you have a function like f of x, you can take a derivative df, oh my bad, not capital F, df dx. And it tells us how rapidly f is changing when you change x by a little bit, right? That's what it tells you. And I noticed that this is a capital D, okay? We call this kind of derivative a total derivative, right? With a capital D, as opposed to a partial derivative, right? So we also call this, I'm gonna now erase this and say this is not just the derivative, because when you're not dealing with partials, you don't even care and you just call it the derivative, right? Or when you're dealing with functions of one variable. So this is the ordinary or total derivative. Okay, so either one of those, but total is in contrast to partial, right? Okay. Now, a total derivative of a function of one variable is no different than the partial. So if I wrote down, if I have my f of x, notice it only has one variable and then one independent variable, which is x, right? So if I write down, the partial derivative, so partial derivative is written like this, partial f, partial x, because f only depends on one thing, not x, y, and z, or x, t, and u, or whatever it might depend on, it's the same as the total derivative. Okay, so those two symbols are interchangeable, right? So, but always when you're working in your theoretical calculations or whatever you're doing, if you have a partial derivative of something that only has one variable, rewrite it as a total derivative, okay? Because it can be confusing, because you might be like, wait a minute, that partial, what does that thing depend on? Because it's really only used when you have more than one independent variable, like x, y, z, or whatever, right? Does this make sense? So always write it as the total, but in the case where it only has one variable, it's the same. Okay, all right. So partial derivative is in contrast to total derivative. Okay, all right. Well, if we look at a function that has more than one independent variable, that's because now if we move into 3D, certainly, right? Like, let's think about, say, the temperature in this room, right? The temperature in this room as a function of position. It's not the same everywhere. If you're over by the heater, which should be on low, it's going to be hotter, right? Then right by the door, et cetera, right? So it is a function of the x, y, and z coordinate in this room. Yeah. So let's look at that. So if we have a function of, let's say, 3 variables, and we'll make one up here, which is the temperature in the room, I would guess that it's a function of all 3 variables, right? X, Y, and Z, all 3 positions, because you vary any one of those, you're going to have a slightly different temperature, right? Okay, now is that a vector, T? Would you say I could write a vector sign over that? What do you think? Yeah, is there a direction to temperature? No. Now, if you're asking something different, if you're asking in what direction does the temperature change, do you think that would be a vector? Sure, right? So imagine asking, what happens as you go from, let's say that's Y, this is X, this is Z, right? So Y, X, no, X, Y, I'm trying to do it for the camera, Y and Z, right? Then you would imagine it's probably colder at the bottom than it is at the top, and that there's some gradient in temperature, right? and that you could draw an arrow to represent the direction in which that is getting bigger, right? That the temperature is getting higher. You could draw an arrow. It's probably an arrow going up. Yeah. Okay. So so that is the idea behind the gradient, right? That again, we all know and love from vector calculus. By the way, what other classes have you used vector calculus in? Like, you know, Calc 3. You did 116 at all? No, well, you didn't take the divergence of anything in 116 or? Okay, maybe in modern physics. But we didn't do it in quantum 1. Yeah, maybe and maybe we did some 3D work in. Yeah, we did some partial derivatives in thermal for sure. So we only really did derivatives. We do like divergences or gradients. So I remember what I remember. Oh, there you go. Maybe he did. Right. Okay. Well, you're gonna get a lot more familiar with it now. Okay. But okay, how does T vary? If you wanted to know, like, how does the temperature vary in this room? It has an infinite number of answers, doesn't it? Because you got to ask along what direction, right? So there's an infinitely many different directions in this room, aren't there? Yeah. So, but we can deal with this. So what we do is we write down a total derivative for this, which asks, you know, what is the change in temperature along each of the directions, right? And then, of course, you can look at that variance along any direction then once you know that if you move X, it does this thing. If you move along Y, the temperature does this. If you move along Z, the temperature does this, right? Okay, and that is where we're going. We're going to the gradient, so it's what we're trying to get to. Okay. All right. So we're not going to write down the gradient yet. We're going to derive the gradient from thinking about how this function changes in all the different directions. Okay. So let's write a total derivative, dt. Total derivative is equal to I'm just writing it down for you. This is actually the definition of the total derivative for functions that have more than one variable. Okay, so I'll show you what I mean. Okay, and then plus, let me finish writing it and I'll explain a little bit. These are partial derivatives. Now think about if t was just a function of x, right? Then this dt dx, so notice here you'd have big dt and you could divide by dx, and this would just be the statement that dt dx is equal to dt dx, right? Because that partial becomes a full, so it's like kind of a dumb equation, right? But if t, like in our case, and my computer is going nuts, can you hear it? It's like, you know, can you let me see 1 second? Because sometimes when it does this, it starts like draining the battery like crazy. It's still charging, so hopefully it'll. All right, we're having technology issues today. I've got to get the activity monitor up and see if there's something I can kill. Everything is so slow. Activity monitor, what happened to you? What's using all the CPU? I guess Zoom. Yeah, I've got it here too. Firefox. Am I using Firefox at all right now? Yeah, no, I mean, I'm not using it right now, like using it. So I can force quit this, I think. Where's the force quit thing?
At least on mine.
Mm-mm.
And then it's just split. On the shoe.
All right, let me just, I'm sorry about this, guys. It just doesn't want to quit. I'm not messing with it. Where's MATLAB? I'm just gonna kill it just in case it's doing anything. Mhm. All right, in Zoom, I can't do anything about. Yeah. Okay. Let's hope this calms it down. This computer's had this problem since it was new. Okay. All right. But now we have the change in each of the directions, right? So remember what a partial derivative is? It means that you hold everything else constant. So if you're taking the partial derivative with respect to y, if there's x's in your equation, you don't take derivatives. It's you pretend the x is a number like 3. Okay? Got it? All right. So let's keep going. So we're not really at the okay, there's another way I can write this. Okay? So I can write this as partial t partial x in the x hat direction. So now I'm making a vector out of it, partial t partial y in the y hat direction plus partial t partial z in the z hat direction. And then dot with dx times x hat plus dy times y hat plus dz times z hat. Yeah. So notice that all I did was just make up a vector that I could dot with this dx vector. That vector dx is actually a vector called dr. So this is really dr. This thing. Okay, FYI, we don't need that right now, but yeah. Well, we will write that out. Okay. And now I can define the gradient because I hope maybe some of you recognize that the gradient is that first term. Right? That's the definition of gradient, and it is a vector. Okay. And it's so this is gradient of our temperature variable dot dr. Okay. Yeah. Okay, so the idea is that you now have this vector that tells you how t changes in each of those directions, right? Okay. All right, cool. So what this is a vector, what direction does it actually point in? Anyone remember? Yeah, and let's take a look. Yeah, let's take a look at why that's the case. Okay, I'm just going to copy this layer. All right, I'm going to get rid of the stuff up here. We can move up here a little bit, do a little bit more work. Okay, all right. So we have a dot product here for dt, right? So dt is this dot product, the gradient of t dot the dr. All right. Well, we know that if and notice that dt is a scalar, right? It's not a vector, dt. So just because we have a dot product. So what is it? Well, it's the magnitude of the gradient times the magnitude of dr times the cosine of theta, which is the angle between the gradient and dr, right? All right, dr is an infinitesimal distance. We can just fix it to be fixed and we're not going to worry about how big dr is. It's an infinitesimal, right? Yeah, that makes sense to you. It's not going to be like wildly big or wildly small. It's, well, this is going to be a small thing that we don't care about how big it is. Okay, hope that makes sense. And now let's look around in theta, right? To see when is dt a maximum. Well, dt is a maximum when cosine theta, so dt is maximal when cosine theta equal 1, or when theta equal 0, right? So the gradient points in the direction of the maximum dt, right? The maximum change, right? Does that make sense? Yeah, cool. Okay. And the magnitude of the gradient gives us the rate of change along that maximal direction. Yeah. Yeah. So let's see. I think I have a sheet. Let me just see what the time is, because, and again, I don't have time on the computer. Well, maybe I do. Thank you. And we have till 12:10. Yes?
Yes.
Yes, and then you go to super. Let me see what I've got here. See if I have time. Well, 20. You're like, what? What? Yeah, we do. We do. We do. There. No. Okay. Well, I'm just trying to decide if we have time for this example. I think we should do it. All right. Everybody get the gradient so far? Okay. Can you take the gradient of a vector? Shauna says yes. Let's just look at the actual, let's just do the notation. We'll give you a clue. Okay. So what if I tried to take the gradient of a vector? That would be kind of like writing like a, or sorry,
Yeah.
it's not redundant, but I kind of know what you're getting at. Like if I had B, A, like this,
Yeah.
because even like B times A doesn't make sense. Yes, if you have a dot or an inner product, yes. So this, in fact, is defined. It's not called the gradient, though. It's called the divergence, right? We'll get there. Not there. Okay. Okay, just being clear, you don't take the gradient of a vector. Okay. We might see stuff that kind of looks like that, but it's very, you'll see what that means. Okay. Doesn't mean dot product or just timesing or something. Okay. All right, let's do an example. So imagine you're standing on a hill. We want to find the direction of steepest ascent, right? So steepest, you're trying, well, direction of gradients, the direction of the gradient, right? We want to see how steep it is. I think you should be standing in front of a hill to get the steepest ascent and on top of the hill to get the steepest descent. But anyway, either way, right? Okay. So let's see. How do we do that? On a hill. Want to get direction of steepest descent, right? How do you get down, right? Or how do you, what do you avoid? Because you probably don't want the one where it's the steepest down, right? That's my guess. Okay. Okay. All right, let's say that the hill has a height function. Z, so that's the height. So let's imagine that the hill has, you know, X, Y, and then Z is the height of the hill, right? Is a function, and I'll use it H of X and Y, so only 2D, that looks like this. 4x cubed minus 2y squared minus 12xy in meters. Okay. So this just means that, you know, if you knew which way you're moving in X and Y, right? It's like you would know how to shade a topographical map or something, right? This makes sense to you? Yeah. Does it make sense that it's only a function of X and Y? Yeah. All right, good. All right. So let's see. Let's try to do a, where is the top of the hill? So let's say you were not standing on top of it, but you're standing at the bottom and you want to know, you know this function, but you want to know where's the top of the hill. Or you're making a map for somebody, you're trying to color in that top. Where's the top located? Okay, anyone have an idea how we would get the top? They're called a critical point. What's it called? Yeah, it's the max, right? And how do I do that? Ah, yes, but how do we take a derivative of more than one? Do the gradient and set equal to 0. That's right. That's right. So we're going to take this of h and equal to 0. Okay, so this means that I have to take partial h, partial x in the x hat direction, and then plus partial h, partial y in the y hat direction, right? And I don't have a z, so that's it. And so I just literally take those derivatives. So let's practice. All right, who wants to tell me partial h, partial x? Read it off. 12x squared.
Minus 12y.
Indeed, good. Okay, so that is our first term. That's time x hat. And then plus, give me partial h, partial y, somebody else. Daniel, Julia, go for it. Well, you can look at the board instead of writing. Okay, minus 4y, good. Minus 12x, good. Excellent. All right, good. Now this is all equal to 0. And the x hat and the y hat are independent. So those coefficients better independently go to 0. Yeah? Okay. So that means we have 12x squared minus 12y equals 0. And minus 4y minus 12x equals 0. In other words, two equations, two unknowns, and I hope you'll forgive me for skipping the algebra to get the answers for those two. That's okay with you? Okay. It's you know, it's easy, but I don't waste your time by doing it. I know that you could all solve two equations for two unknowns. Yeah. Okay. All right. So the answer for the location is, let me see, did I write it actually down or did I something? Oh, yeah. You know, I think we actually have to do this because we have a square in there and that makes it a little bit more complicated. It's kind of a pain in the butt. Okay. So that kind of sucks. All right. So let's see. So let's look at this guy. And so we're doing this guy here, and let's solve for x. So x is going to be 4y over 12. Indeed, yes, guys. Negative 4y over 12. Am I right?
Yeah.
Check my algebra, and that's negative y over 3. Okay, cool. So we can now plug that into the top equation. All right. So we have when, so we have 12. And then we have negative y over 3 squared minus 12y equals 0. Okay, so let me just do a little algebra on that. So this is going to be minus, sorry, no, y, and then 12 over 9, right? Minus 12y. This is squared, my bad. Yeah, thank you for catching that. Yeah, get rid of the 12s because this is all equal to 0, right? So we can just goodbye 12s. Yeah. And then we can write this as y times y over 9 minus 1 equals 0, which means that that's either y equals 0 or y equals 9. So 2 answers for y. Yeah. Good. Now we also have 2 answers for x because x is written in terms of y now, right? In the yellow equation. So we also have 2 answers for x. So when y is 0, notice that x is 0. So these are a pair. This is a point. All right. And then when y is 9, then x is, let's see, not, oh, minus 9 over 3, minus 3. And these are a pair. Yeah. Okay, now we actually don't know which one of those is the max, do we? What do we do next? Hmm? Yeah, absolutely. Plug them in and see which one's the max. Yeah. Indeed. Okay, so let's do that. I'm going to erase some of this stuff up here. Let's see. We have no room really. Let's see. I'll go this. Move this. And I'll move the statement of the problem because we know what that height function means. And we'll have a little room up top. All right. So let's do that first point first, right? So we're going to do x. So the point, let's do our point. Hey, already done, huh?
Yeah.
Point 0, 0. Yeah. All right, so for point 0, 0, that's pretty easy. H is 0. Okay, most likely that's not the maximum, is my guess. That's probably the bottom of the hill or something. Yeah, I would assume. Okay, so the bottom is at 0, 0, 0. It's kind of weird, but okay. All right, and then for point -3, 9. I'm not doing my color coding, sorry. We got to do a little work. Okay, H is equal to 4 times, what's, 27, 3, okay. The negative, thank you, okay. Minus 2 times y squared. Oh, yuckers, this is yucky. Minus 12 times -3 times 9. Right, whatever. I think I wrote that down somewhere. 54 meters. This is 0 meters. Okay. So that's the maximum, obviously. So the point -39 is the max. And if we ask how high is the hill, it's 54 meters high, right? Because people always mean at the highest point. They don't mean at other points on the hill. They mean, what's the highest point on that hill? Right? Okay. All right. So we could also use the gradient to just figure out, like, you know, how steep it is, right, originally, but I think we're going to skip that part. Okay. All right. All right. So one thing I want to mention that's super important about gradients is that and you should always think from now on as of derivatives as differential operators. Okay. Now I know that if you've taken quantum, which I think all of you have, you are familiar with this. That's the momentum operator, has a differential operator, right? But you can think of all derivatives as being differential operators that are linear operators that operate on things, right? It's kind of a slightly more sophisticated way to think about that. Okay, so you can think of any derivative, my bad, derivative as a differential operator. So for the gradient, very useful to think of that is just by itself, just hanging out by itself. And it gets applied to things. And when you apply it to things, the form that is convenient is you put the x hat, the vector part, before the derivative, so it doesn't get confusing that somehow you're operating on the x hat. Now in Cartesian coordinates, x hat doesn't change. It doesn't have a derivative. It's like a constant. But in curvilinear coordinates, we discussed how the vector direction changes, and it does have a derivative. So then it becomes really important to remember to put your unit vectors before, just so you're not confusing yourself when you're going to apply this differential operator to something. Okay, so then we would write partial x plus y hat partial y plus z hat partial z, yeah? Okay, so when we apply it, then it just looks like a regular gradient again, right? And then those x hats can go everywhere you want, but it's when you're writing the differential operator, you want to write it in this form. And I want to point out that one notation that I use a lot and may or may not use in this class is this notation. Instead of writing that whole derivative, which is a pain in the butt, I write this little shorthand for the derivative, for the partial derivative. It's only used for the partial derivative. I never use it. Never use a shorthand for the total derivative. Okay, it's just a little subscript that means which partial it's right. Okay, now we discussed that this thing. Oh, I should tell you, if you didn't already know, this is called del. Some people call it nabla. If you are trying to write this in LaTeX on, overleaf, it's \nabla. I don't really understand why, but okay. But yeah, nabla is used, and sometimes I may even say that, but I call it del. Okay, and it is an operator. Okay, so the gradient, right? Gradient is del operating on a scalar function, right? Okay, so like del t, and what you get out of it is a vector, right? Okay. And then you can do this, we just discussed, you can act del on a vector. Okay, there are two ways to do that. So there's one here that we're going to say via the dot product. Okay, and that would be the divergence. That's called the divergence. So I should have put divergence here first. Sorry, my bad. Del dot A, divergence. And the third thing is act del on a vector via the cross product. Because remember, there are two vector products that we know about. The dot product results in a scalar, and the cross product that results in a vector. And so this would be del cross A, and this is called the curl. Okay. Okay, let's look at these and let's see what time it is. I realized I could pull my mouse up and see what time it is. Okay. Okay. Let's look at these each of these. Okay. Let's look at you've seen the gradient. So let's look at, oh, I want to back up for 1 second because I want to remind you that gradient is called just grad sometimes. And divergence is called just div sometimes. And curl is just called curl. Nobody shortens curl. And the reason is sometimes there are these rules that we're going to learn about, right? Like curl grad equals 0. Okay, that means that if you take that curl of the gradient, because the gradient's a vector, gradient of something is a vector, right? You will get 0 no matter what you're taking the gradient of. Okay, so there's things like that that we use these kind of shortened terms for. Okay, all right, let's go back to all right, so let's look at divergence. Not divergence. 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 Okay. Divergence. Okay. So what does that look like? Well, we know what del is, right? It's this differential operator. Yeah. And we dot it with a vector. And so a vector A looks like this. A equals x hat plus y hat plus z hat. Yeah. Let me move this a little bit. So by the rules of dot products, right, I'm applying that del to the vector A, but because we have unit vectors, we went through this yesterday, right? X hat dot x hat is 1, but x hat dot y hat is 0. So what ends up happening is that you're only applying those derivatives to their to the components that match the derivatives independent variable, like ddx of ax, right, is one of the terms. Never ddx of ay or az. Okay, so this ends up being partial ax partial x plus partial ay partial y plus partial az partial z. Okay, fine. So what does it mean? Well, let's just draw some pictures that might be helpful. So we'll draw a picture of, you can think of this as the electric field of something, a little charge or something, whatever you want to think of it as. And then these vectors get. So maybe it's not the electric field because that would be diagonals, but whatever. It should be spherically symmetric. I'm really bad at drawing, as you all know. Okay, so this has a large positive divergence. What is represented by those arrows? Any idea? Like, well, may or may not be the electric field. You're on the right track, though. Remember, this is the divergence. What's its divergence of? Well, for example, huh? So, okay, well, let's back up a second. We are, remember that this, when I write down divergence, I'm really thinking about a function, right? Look at the derivatives. There are derivatives of the, like d partial ax partial x. Why do I need a partial derivative? Because the assumption here is that A is a vector field that everywhere in space, there's a little vector, has a certain length, has a certain direction, right? Okay, so if you think about A as being a vector field, Okay, that means everywhere in space there's an A. There's one. Right, A of X, Y, Z. And then I move over here, and there's maybe one that maybe goes down here, that's much longer. Right? X1, Y1, Z1. This is A of X2, Y2, Z2, whatever it does. This is not the same A I'm drawing here, right? This A from my terrible drawing that I'm drawing here is a vector field that starts off near the center of this thing here, right? Near the center, and it gets bigger as you move out. So that's why it wouldn't be an electric field, okay? Right, but this is an example of a really pure field where it's very easy to define. As you go far away, the vectors get bigger and bigger and bigger, right? It's spherically symmetric. Think of this as being in 3D. If you took the divergence of this vector field, you would get a large positive divergence. So think of it as diverging, those vectors are diverging from each other, right? And growing, right? Does that make sense? Okay, what about something that has zero divergence? You could have something that would be a vector field that would look like just everywhere in space, it's the exact same direction, the exact same length. I'm not drawing them the same length. The exact same length. And this would be like, I don't know, a good approximation for near, near an open window, right? Far away from an open window, the wind's going to die out, but near, say you have a lot of wind coming in through an open window, very close to it, all the wind's going in the same direction at the same speed, and so the vector field of the flow of air would maybe look like something like this. That's the charge, though. You mean the electric field?
Yeah.
Yeah, like, yes, absolutely, yes, and of course, that's an approximation, but stay away from the edges. Yes, yeah, absolutely, yeah. So this would be zero divergence. Okay, and then just a positive divergence that doesn't look like this spherically symmetric, you can certainly have, right? So you could have like, something that's just changing very uniformly, though. So little tiny vectors down here, a little bit bigger here, a little bit bigger here, and a little bit bigger here, right? So it's changing. Yeah. So this would have a positive divergence. So it's not like you have to have this radial spread to have a positive divergence, right? Yeah. Okay. Let's go on to the curl. So again, think of a vector field A. Okay. Everywhere, so that everywhere there's a little vector pointing in some direction, you can take the curl. Okay, and this becomes a vector, right? So it returns a vector, doesn't become a vector, sorry. It returns a vector. It's a function of two vectors, one being the differential operator and one being the vector field, right? So if we were going to do this with the determinant method, right, we would do this. Right? So we would say, let's do it with the determinant method. It would be X hat, Y hat, Z hat here. It would be partial X here, partial Y here, partial Z, and then it would be AX, AY, AZ. Yeah, and then you would do those determinants and you would get your curl, right? Where those little differentials are ddx, ddy, ddz, right? And they would apply onto, right? When you do that, when you calculate, if you want to calculate the very first one, let's do it. Let's just do the X hat component. Okay, the X hat component. Remember that I kind of cross out these two little guys here. And I get the determinant of this partial matrix here. So that's going to be partial y acting on AZ minus, now be careful here, right? We got to put the derivative in the front. Partial Z acting on AY, right? That's what that is. And then write it one more time and then plus ... for the other two components, right? So equals X hat and then partial AZ partial Y, just writing it out, minus partial AY partial Z. Okay. All right, now we know that we can write this in terms of the Levi-Civita tensor, and this becomes really useful when we start doing like second derivatives and stuff like that and proving identities. So I'll write out just the component in terms of the Levi-Civita tensor, and it's not really any different than you've seen for just the regular cross product. But if I want to write the component del cross A, like the ith component is Levi-Civita I, J, K, and then del J, A, K, where that del J means D, D, X1, X2, or whatever, right? This is the very useful part of that notation, that little del notation, is that it's confusing if I try to write that as D, D, X something, because you're like, wait, X? Is it X, Y? What do I put? It becomes really useful to just use that notation because D, J, right? I can be like, okay, D1 is partial X. D2 is partial Y. D3 is partial Z, right? Just a quick notation for that. Okay. All right. So curl is a measure of really how much the vector field curls around. That's why it's called curl. Curls around a point in question. Right? So like think about water circling the drain or the rotation of a galaxy, right? So the vector field there would be the velocity field of the stars in the galaxy. Yeah. Or you know, a hurricane. So many examples of curl, right? Okay. So if we look at a vector field, so imagine you have a vector field that looks like this, and you know, it's the vectors are not supposed to be curved, right? But they just go, you know, vectors are straight. Okay, just to be clear, but the vector field, they're changing direction in such a way that it kind of spirals around, right? Yeah, and there's the center point. Okay, this has a non-zero curl for sure. Okay, and as we'll find out, that there are things that have zero curl. In fact, the electric field has zero curl. I don't care what charges you put together. There is no charge configuration that you could put together, not how hard you try, to give the electric field a non-zero curl. The electric field has curl zero. Really fundamental property. What do you think about the magnetic field? Do you think it has curl zero? What you guess? It has zero curl or not zero curl?
I would say
Non-zero curl. The quintessential example of an electric field, sorry, magnetic field, is think of a current wire just going straight up, right? And then it's going to curl the vector field for the magnetic field is those little vectors, just like I've drawn here. That doesn't spiral out, but like, yeah, curl of magnetic field is not necessarily zero. Okay. All right, let's see. We have all kinds of product rules because we have now 3 types of new derivatives that are vector derivatives, right? Well, the gradient turns something into a vector, so you got to consider it, right? And then you have the divergence and you have the curl, and we know product rule in general for regular derivatives, but for vector derivatives, it actually becomes a kind of a pain in the butt. It's easier to kind of go look those up than to remember them. FYI. Yeah. I don't know why my thing just moved. Give me a second. This program is like a little mystery. Okay. Again, I told you, endless complaining about the program. Can't help myself. Next. Okay. Let's look at the regular old product rule, right? That we know and love. That's an easy. So we just take a regular old derivative. So regular Prod rule, okay, is d of fg dx is df dx times g plus dg dx times f, right? So everybody knows and loves that. Okay, right, everybody? Okay. So for gradient, it's not too different. It's actually not too different. Okay, that's pretty nice. And you can prove this to yourselves, right? By writing out a gradient and using this rule to get you to the answer for gradient, but it's very similar. Okay, so for gradients, it's easy. Gradient product rule is the gradient of f times g, and these are scalar functions, otherwise we're not doing this, right? We're not taking a gradient of it. Okay, and it's very simple, okay? It's the gradient of f times g, I'll put the g over here, plus the f times the gradient of g. So it looks just like that product rule, okay? Okay, now let's make it a little more complicated. Because remember that if I take two vectors and I do the dot product of two vectors, I also get a scalar. And couldn't I take the gradient of that scalar? So in other words, couldn't I do this? Grad of A dot B, where A and B are vector fields as functions of X, Y, and Z. Couldn't I do that? Because A dot B is a scalar function, whatever it is. Yeah? Okay. So, all right, well, what do I do with product rule here? Well, here's where it gets fun. Okay. Any guesses to what this is?
So the gradient thing, they turn a scalar into vector. And they're taking the gradient of the dot product of vectors.
Yeah. Because that's a scalar, right?
Yeah,
Let me just write a little example out here. Like this is if A is X times X hat plus Y hat, which is 2D. And B is, Y X hat plus Z, or whatever, so not Z, not Z, X, Y hat. And A dot B is X, Y plus X, Y equal to X, Y. It's a scalar. Yeah?
yes.
Yeah. All right, so I can take the gradient of it. All right, but let's say I'm not using this example. I just want a general formula, like a general product rule, like the ones above here, the yellow and the pink. Any guesses? Not hard, huh? Then what do? You can't take the gradient of a vector. Excuse me. You can't take a gradient of a vector. Oh, okay. Well, here it is. You're not going to like it. Okay. A cross the curl of B plus B cross the curl of A plus A dot del acting on the vector B plus B dot del acting on the vector A. Told you we're gonna like it. That is ugly as crap, right? Okay, so these product rules can get nasty. All right, so let's just look at one of these because it's probably like, I think you all can understand A cross del cross B, because you take the curl of B and then you do another cross product with the answer, right, with A, right? Okay, you can all do that. But what is A dot del acting on B? So let's think about that. So we know that A, so I'm going to erase that over here. I'm just going to write A again in its general form, just like some random field. So A is AX, so some function XYZ that, my bad, X hat plus A Y y hat plus a z hat, right? Where each of those are functions of x, y, and z, okay? And let's let b, similar thing, b x hat plus b y hat plus b z hat, yeah? Okay, so let's see, what is a dot del? Let's just calculate what's a dot del. Remember what del is? Let's write del up here. Del is x hat partial x plus y hat partial y plus z hat partial z. Okay. So the del is not acting on the a. Let's be careful. It is not acting. It is not. Okay. So what do we write here? We write a x partial x plus a y partial y plus a z partial z. Notice those derivatives are not acting on a. The del is on the other side of a. Now that a dot del is now a differential operator, isn't it? It can be applied to b. But what you get out of it is a vector, right? You have to get a vector because the gradient of a scalar is a vector, right? So when you apply this to b, that differential operator gets applied to every component of b. Okay, so a dot del acting on b now is, let's write it out, a x partial x, excuse me, plus a y partial y plus a z partial z. And then we have the b vector, bx x hat plus by hat plus bz hat. And now there's no dot product here. It's you literally have to just apply each one of those derivatives to each one of those components. So let's look at the first term here. I'm going to do a little kind of foil here where we're going to apply this first thing to this whole business. Okay, so I would get AX, and then I would get, the first thing is going to be the partial of X acting on BX. X hat, if X hat was not, if this was like a different coordinate system, I would have to worry about the derivative of X hat, and I would have to use product rule and also take its derivative. But X hat doesn't have any derivative, it's like a constant. Okay, so we don't care about the fact that it's BX times X hat, right? You understand what I'm saying? Okay. So now this becomes partial BX partial X, right? For that first term. And then plus, I'm still acting my AX on this whole thing. Oh, I'm sorry, I left my X hat out. Times X hat, right? Times X hat, okay? And then plus AX partial BY partial X times Y hat, right? Plus AX partial BZ partial X times Z hat. And then I would have to go on and do the rest. Like when I apply the, oh, that's green. That was a bad color choice. I'm sorry. Like here, right? I would have to apply this guy to this whole thing. And I get a bunch of more terms. And then I could collect all the X hat, things that are proportional to X hat, and all things proportional to Y hat to get all the components. But that's what A dot del is. So this is the ugliest of the product rules, I think. Yeah. Yes, yes, it's terrible. It's absolutely terrible. It's absolutely terrible. I think, I can't remember that in the video, I think I have a video that's like the rest that proves this using the Levi-Civita tensor. This is where this becomes really useful. What time is it now? Okay, so we're almost done, yeah. So I will put that video up. You could watch it or not. I'm pretty sure that, yeah, it goes over a couple of things. Maybe you should watch it because, I mean, we're basically done, but yeah. Let me go through one more thing before, and I won't prove this. I think that's on the video. But it's fun because this is where the Levi-Civita tensor and all the index gymnastics that we do really shines. Okay. All right. Let's look at this though. Let's look at some rules. So we have del dot grad So if you take the divergence of a gradient, div grad, okay, you don't necessarily get zero. This is fine. Good. This is good. Sometimes non-zero. So for instance, right, we might take the divergence of an electric field. An electric field is given by grad of a potential, right, scalar potential. And it's no problem. You can take the divergence of an electric field. Yeah. You might get zero, you might not. However, if you take the curl of a gradient, you always get zero. This is curl grad. Zero, always. Does not matter what that t is, does not matter. Okay, 3. You could take grad of a divergence, because the divergence is a scalar, right? This is a dot product. No problem. You don't get zero. You could be zero, could not be zero, sometimes non-zero, or sometimes zero, but you know, in general, sometimes non-zero. Okay. This would be like taking the gradient of the flux of an electric field. There's no reason you couldn't do that, right? Okay. All right. But if we take the divergence of a curl, we get zero. This is div curl equals 0. Okay. So what this tells us actually is that well, you won't know this for a bit, but there's something called the vector potential. And if you take the curl of the vector potential, you get the magnetic field. Okay. And the divergence of the magnetic field is always 0. And this is the statement that there are no magnetic monopoles. That's what that means, right? You can't have, when you take one of your fridge magnets and you break it in half, you still get a north and south pole. You don't like all of a sudden get one north pole over here in this hand and one south pole in this hand, right? There are no magnetic monopoles. That's because the divergence of B is always 0, which means that if you take a magnet, right, and you put it, and all the field lines, if they go out, they come right back in. So if you calculate the divergence through a surface, right, the flux through a surface, it's always going to be 0, because whatever goes out comes right back in at some point, right? Okay, so there's that. And then, of course, there's curl, and there's absolutely nothing wrong with taking a curl. Meaning it's sometimes non-zero, right? There's no. I'm saying it this way because I'm just trying to point out that it's not always 0, right? It can be other things. And this would be like taking the curl of a magnetic field. No problem with that. All right. Yep. All right, we'll see some of you in super class. Let me kill the Zoom, stop share.